Okay, in this video we're going to discuss the data that was collected during a practical session and how to interpret isokinetic data. There's a lot of information here. Believe it or not, this is a patient's report, the actual report that you could get if you were doing research with it. It contains even more information. It can be a bit overwhelming, but we'll start off with this. If you recall, here we have the 360 degree per second test results for flexion extension, 180 degree per second, and down here on its own the results for the 60 degree per second test. So you can think of this as slow, medium here on the right, and fast on the left. And obviously this was, as you can see here, a concentric knee flexion extension test, or isokinetic test, I suppose I should say. There were 10 repetitions performed for the 360 degree test, 5 for the 180, and 3 for the 60 degree per second. I will double check that, but I'm almost certain. Yes. Excellent. So, let's start with the 360 degree per second results. Now, we're starting this example, assuming nothing about our participant. However, this is the first thing that you would want to factor in deciding which results to pay attention to. So, a strength athlete would be more interested in these results, these slow results, the 60 degrees per second. In fact, you might not even perform the other tests above. However, if you have someone in a sporting environment, well, we would use a higher angular velocity, but we would be interested in the faster movements, essentially. So there's a lot of things to consider before you, about the participant or about the athlete before you begin, but we'll assume nothing. We will just look at the results as they are and see what we can make of them. So peak torque, as you can see, there is a deficit of 10.7%. Now this is just above what we would consider to be a just normal everyday deficit, the sort of bilateral asymmetry that occurs in daily activities, that just because you have a dominant side. Now, this particular person was, their right side was their dominant side, and it's also the injured side, the previously injured side. So that is quite telling and could potentially be indicative of an issue, an underlying issue here, and that perhaps that condition hasn't fully healed. So let's look at some of the other data. As if you've read the previous section, or the previous page within this section, I should say, you'll know that this 10.7% for peak torque is somewhat misleading because it ignores these two values here, ignore the other 9 repetitions that were performed. Peak torque generally occurs during the first set, and therefore if we look at peak torque, we're simply just, it's almost like disregarding everything else that took place in the test. You might as well have just done 1 repetition. Well, we didn't, we did 10. So for my money, and this isn't based on anything that I've read, but more just common sense, average peak torque is going to give you a more holistic overview of that athlete's performance during a set. And as I say, if you watched or read the previous section, you'll know that the deficit here is about 2 something percent, so not normal, within normative values. A peak value is by definition an outlier, and therefore not always the most useful to go by. So I wouldn't pay too much attention. I wouldn't worry about this too much here. Peak torque as a percentage of body weight. Well, this is okay if we have someone else to compare it to, if we have another participant, but as we don't, we're just going to skip past that. Max rep total work. So we have covered work and power in the previous sections. So, and my thoughts on those measurements being in there. Essentially, as we said, work and power are directly correlated. If work goes up, power will go up. The values won't be the same, but the relative increase or decrease will be. And so there's no point. You might as well just show one or the other. There's no benefit from showing two. So cynical side of me always thinks that, well, I think they've just included, instead of just reporting work and power, it's maximum rep total work and average power, which will give you different values but are derived from the same thing. I think it's just a way of adding more numbers personally, but there we are. So maximum rep total work, this is kind of like peak torque in a way. So it is simply a measurement of the repetition where the greatest amount of work took place. So again, that will most probably be the first repetition or the first set, and measuring the total work that was performed within that set or that repetition for each muscle group. So the difference or deficit, I should say, will usually be similar to peak torque. I would say out of the two that max rep total work is the more useful of the two measurements than peak torque, based on what we've covered on the previous section. But it's, as I say, it's a way of adding a few more numbers really. So coefficient of variance, there we haven't covered this previously. This is a measure of the reproducibility of the test that has been performed. So basically, if the participant were to perform the test again, the exact same situation, how likely is it that they would get the same results? Essentially, it's a percentage measure of the quality of the test that's been performed. So for off the top of my head, I think large muscle groups, so such as the quadriceps and hamstrings, anything under 15% is what we're really looking for, and I think for smaller muscle groups 20. So this shows a larger than acceptable coefficient of variance, but there could be many reasons for this. It could be the participant was in pain when performing the test. It could be a lack of experience, could be a lack of instruction or poor instruction. Could be apprehension on their part, so their first few repetitions weren't as good as they should have been, perhaps, or simply a lack of effort. They're just not trying hard enough. So it's hard to pin down what this value really means in terms of how can I use this? And the best thing to do is simply to make sure that the test is performed in as effective way as possible, to make sure that we basically cover all the points that we covered during the practical session. And as long as you've done everything you can in the setup, then that's the main thing to focus on. Then you can start to rule out, well, did I set the chair up right? Was the dynamometer head in the correct place? Did I replicate that well on the other limb? And sometimes you will even see this come down with experience, the coefficient of variance. So as long as you've set the test up correctly, you've set the chair up and the participant is in the right position, everything's good to go, then coefficient of variance can be linked more to the participant themselves and that there's something going on. So I would assume, based on this, that it was because this was 360 degrees per second was the first test that was performed. 99 times out of 100, when someone's using the Bardex for the first time, particularly at a high angular velocity. The first 3 repetitions, instead of being the strongest, are very often some of the weakest, because you're getting a feel for the speed that you're moving at, and so the peak torque will usually occur in the 4th set or around there. So I would stake my money on that being the issue. So I would assume this to be a lack of familiarization. Average power, as we've discussed, so no big deficit there. We wouldn't worry about that. Total work, likewise. Acceleration and deceleration time. So unfortunately, there are no standardized values to compare this to, but acceleration and deceleration time refers to the time it took in, obviously, milliseconds to reach the angular velocity, so 360 degrees per second, and then to decelerate, to stop, to go from that peak angular velocity to a dead stop. And this is being proposed as a useful measure of neuromuscular performance, so essentially looking at how well you can basically get started. So the ability of the limb to, the ability of the nervous system to recruit muscle fibers as quickly as possible, and then produce the necessary muscular force, which in turn generates a torque and allows the limb to move at the required angular velocity. So in the absence of a comparator from the literature, so we don't have any standardized values, we tend to compare left to right and then compare between different testing speeds to see if this is still present. There isn't a huge, I mean, at the end of the day, you're talking 20 millisecond difference there in both. So that to me isn't something that I would be concerned about. That equates to 0.02 of a second, which isn't going to be a speed that we're going to have any conscious control over, so I would say that that's fine. I wouldn't worry about that at all. Range of motion, so we had 108.3 and 100. Now this is going to very much be determined by the tester, the researcher who sets up the experiment, but then did the participant reach that range of motion throughout the test? So you'll notice here the range of motion was 108, let's say, and 100. Okay, fair enough. But here we have a slight difference. There's 109.5 and 100.6, and in the 60 degrees per second, 10101. So let's say 109. 101, 191 and 18 and 1. So there's been a slight variation between testing, but not enough to warrant concern between tests. So we're talking about degrees, so there's a small variation, but however there is a variation in the range of motion between limbs. Now this shouldn't occur unless, when setting up the away and towards limits, there is a significant difference between the two. However, we would assume this to be, I would interpret this to be a deficit on the right side, and a unconscious or conscious unwillingness, I should say, to reduce the range of motion, perhaps through muscle imbalance, as we said, or underlying pain. You would have to talk to the participant beforehand, but this is certainly something that when they came in for a second test, you would want to bring up that it's very important to reach the full range of motion. Likewise, it could just be an issue with familiarization, but as this is the involved limb that consistently doesn't reach the full range of motion, and assuming that the range of motion was the same between the two tests, then we would be tempted to assume here that, well, perhaps this is linked to this underlying condition, this underlying injury that we have. And average peak torque we've discussed before. I'm going to ignore the agonist-antagonist ratio just for now, and we'll come back to it. So essentially, in terms of extension, I would say that everything here looks okay. There is, however, a deficit, no matter how you look at it, between flexion, between the limbs during flexion. The peak torque deficit during flexion is you can ignore the negative minus sign, it's just done so that you get different, so flexion, extension, positive, negative, depending on the direction, and they color code it accordingly, but you can assume this to be 24.4% deficit, so there is interestingly a stronger right hamstring compared to the left, despite the fact that this was the involved and this is the injured side. Now, again, you would be tempted to think, yeah, but what about the average peak torque? And I have done the math quickly, and it's pretty much the same value, slightly reduced, but that means that this deficit that was seen in the peak values is consistent. It is present all the way through, and that's meaningful. That gives us something important to work with. So we have a significantly stronger right hamstring, or knee flexors, if you like, compared to the left. Now, the reason for this I can only speculate, because we don't know the background. As I said, we're starting with a blank slate here, but nonetheless, it's certainly an issue that would need to be addressed. So as you can see, when comparing left to right, the injured to the healthy, even though we're not using these values, the difference, there is a significant difference between left and right, where the right is producing the higher values, it is the stronger limb between all of our measurements. Peak torque as a percentage of body weight, max rep total work, there's a 15% deficit, or 15.6. We have a better coefficient of variance. Big difference in the coefficient of variance there, not sure why. Average power, total work, again, take those as they are. But note the difference in the acceleration time, the time it took to get to 360 degrees per second. See now, instead of a 0.02 second deficit, we now have a 0.05 second deficit, which again is not a value that you can, in terms of addressing the balance, there's not much you could do, but it is still there, and it is something to be conscious of and that you would want to check throughout the rest of the report. So we would say at this point, okay, we have a significant imbalance in the right and left hamstrings, where the right has become the dominant hamstring. So let's go on. We'll ignore the 180 for now. Go to the 60. So this is the slow test, 60 degrees per second. To be fair, I tend to ignore the the 180 degrees per second test if I can't find anything in the others. For me, 180 is just it's there just in case. I like to use the fast and the slow test, the 360 and the 60 degrees per second. So that's what we'll focus on here. Now, as you can see, quite the deficit here between the left and right. Does this hold true when we look at the average peak torque? Well, yes it does, and then some. The average peak torque deficit during extension came out at more or less, if you round up, 58%. So there is a significant deficit here. So we're starting to see a bit of a pattern. So, but it's interesting in that the left knee extensors seem to be stronger due to, or seem to, let's think about it, that's the wrong way to phrase it. The right knee extensors seem to be weaker due to previous injury. However, we are consistently seeing on the same leg a set of stronger hamstrings on the injured leg. Now, why might this be? Well, this is what we would investigate. So, acceleration time, deceleration time, nothing too much to worry about there. The total work, average power are showing the same thing. It's very consistent. This is a very reproducible test. This is good. In fairness, the coefficient of variance does change depending on the speed of the test, the angular velocity. So at this stage, we would say at both the fast and slow angular velocities, the 360 degrees and the 60 degrees per second, we are seeing a significant reduction in strength, a true bilateral asymmetry between the knee extensors, particularly at a slower speed, or a slower angular velocity, I should say. And this could be for several reasons. This could be because it's taking longer to complete the repetition, therefore there's more discomfort, there's more pain. It could be because of greater demands placed on the muscle to complete the movement, which would be my bet. And from there we then have a reduced value. So with the faster test, because the knee goes from flexion to extension so quickly, there is less of a demand placed on the muscle through the repetition. So here, once again, we have a imbalance between the left and the right, where we have a stronger, I should say, righter hamstring, although it's worth noting that the deficit is not as great in the average peak torque here. So what would we make of this? Well, the reasons for the reduced hamstring, the reduced knee extensor strength would be obvious. It's a simple case of, well, whatever the injury was, and I actually can't remember, it is still causing issues and it needs to be addressed. It's possible, and this is pure speculation here, that the increase in the strength of the right knee flexors, or the injured knee flexors, has occurred as a product of the injury. So you injure your muscle, or you have an injury to an area that the muscle works around, so this muscle doesn't get used so much. You're trying to avoid engaging the muscle, so you still have to maintain joint stability, and it's possible that this increase in strength here has come as a product of that very thing. Muscles co-contract around joints when in an isometric position, so just generating force. So when you're standing upright, your quadriceps and hamstrings are engaged to just maintain the patellofemoral joint and prevent any injury from occurring, just to maintain that joint integrity. If one of those isn't being used due to injury or is being avoided, then there is a greater demand placed on the other. So in this case, the agonist muscle would be our injured muscle, quadriceps, or structures around where the quadriceps work. And in our case here, the antagonist muscle, the hamstrings, have perhaps played a role in trying to maintain that joint integrity. I'm umming and ahhing a bit here because I'm stretching for an answer a bit, but that's possibly the reason why the antagonist has become stronger. I mean, that is a lot stronger, but it's certainly possible. So, what was this value? In fact, I'll just stay here that we sped past earlier. This is the agonist-antagonist ratio. And in terms of a knee flexion extension test, we refer to this as the HQ ratio. So the results are presented under extension. So in this case, the agonist muscles are the knee extensors and the antagonists are the flexors. So we have a value here for the left and right leg. So this is a Uni-Natural analysis looking at the agonist-antagonist pair. And this test uses the peak torque of the right limb on both sides, so for flexion and extension, and divides the hamstring peak torque here, 125.8 by the quadriceps here, and paradoxically then presents it as a percentage here. So it's not really a ratio, it's a percentage, but never mind. We'll just gloss over that to show essentially how strong the agonist is compared to the antagonist. So as we said before, they give you normative values here for certain tests. If the quadriceps were producing 100 Newton meters of torque, then the hamstrings should be producing 61 Newton meters of torque at this angular velocity. Here we've got, and I've not seen this too many times, an almost 1-to-1, almost equal. So that's a real issue that needs to be addressed. Quadriceps should not be equally as strong as the hamstrings. In fact, if you were to compare the average peak torque here, or if you were to divide the average peak torque here by the average peak torque of this, in fact, let me just do that because I'm curious to see what we'll get. We're going to get an odd number. Hang on. So HQ ratio, hamstrings average peak torque is 104.2, and we're dividing that by the quadriceps. You don't usually, the HQ ratio isn't usually based on the average peak torque, but because it's a more reliable outcome measure, let's just do it for fun. And then there's our lovely ratio, and we're going to ruin it by making a percentage. So 127% deficit, because you can see the average peak torque of the hamstrings is greater than the average peak torque of the quadriceps, so there is a significant issue here. Assuming this test was performed correctly, and the coefficient of variance actually says that it was, then this needs addressing. As the HQ ratio, or as the angular velocity increases, so too does the HQ ratio. So at 180 degrees per second, we should see an HQ ratio of 72. For some reason they haven't reported at 360, but that should be around about 82 or 81. So again, in all but one instances. So here we've got a all but one, apart from the right side, there is a uni-natural deficit between the quadriceps and the hamstrings. So this could be adjusted in, or this could be tackled in several ways. Again, this isn't a physio course, so we won't be. So the way to think of this is that reducing the quadriceps strength, or if the quadriceps strength is reduced for whatever reason, will result in a greater HQ ratio. Whereas if we increase the hamstring strength, we will also see an increase in the HQ ratio. So reduce quadriceps strength or increase hamstring strength is what will determine our high HQ ratio. We have a very high HQ ratio here, and it is this reduced quadriceps strength very clearly, as you can see from these deficits. So there is an imbalance present that needs to be addressed, and that is, I would say, I've gone on for half an hour now, due to an issue with the quadriceps. I'll provide some more literature after this. I'm going to wrap it up here because it's quite a lengthy video about the HQ ratio and about isokinetic testing after this video. As always, any queries, feel free to drop me an email.